Hi everyone, my name is Sarah Chamoun and I'll be presenting the final project for this Introduction to Machine Learning course. This project focuses on using machine learning to predict student performance. Our main goal is to predict how students perform based on factors like study time, attendance, and family background. By spotting patterns linked to success or struggles, schools can offer the right help at the right time. This supports things like early intervention, smarter planning, and personalized support. We use data from both math course grade, math final grade scores, and Portuguese final grade scores. We We use the UCI student performance dataset, which includes grades and details like age, gender, and family information. First, we cleaned the data by filling in the missing values or removing bad rows. Then, we encoded text columns into numbers and scaled all numerical values to the same range so the models could learn better. This is a screenshot of the dataset. This summarizes what's inside the data set, such as grades, demographics, lifestyle factors like alcohol use, and school background. It gives a complete picture of both the student. It gives a complete picture of the student both inside and outside the classroom. The models we are using are linear regression, random forest regressor, gradient boosting machines, and neural networks. To improve results, we tune settings such using grid search and randomized search, and we also use cross validation to check how well models perform on different data splits. Linear regression, it's the simplest model. It draws a straight line to fit the data. It's easy to interpret but can miss complex patterns. Random forest builds many decision trees and combines their results. It's accurate, handles nonlinear relationships well, and avoids overfitting. Gradient boosting builds trees one after another, improving each step. It can be very powerful but needs careful tuning to avoid overfitting. And neural networks tries to learn patterns by mimicking how the brain works. They're good for complex data but need a lot of data to perform well, and our data set was a bit too small. I tried increasing the R2 score of the neural network and I didn't go anywhere because the data set wasn't complex enough. As you can see, I put screenshots of my code. I need to work on narrowing the libraries needed to import. I will do that moving forward after this course and semester ends. You input the files, you process the files, you see the first 5 rows of data per each file, and I created new variables such as average grade and grade growth. Average grade calculates the average of the first 2 grades, G1 and G2. It gives a sense of how the student has been performing before the final exam. And grade growth, it measures the change in performance between the first and second grading periods. A positive value means the student improved, while a negative value means their performance dropped. Both of these features were added to give the model more insight into student progress, not just the final score. And here you can see that I did data pre-processing. Before we could train any models, we had to clean the data and prepare the data, a step called pre-processing. The data set had over 30 columns, including student demographics, family background, school support, and academic history. We started by checking for missing values. Some rows were incomplete, so we either filled them in using techniques like imputation or removed them if they were too sparse. Next, we had to convert text into numbers so our models could understand the data. For example, a school column had values like GP and MS, and we converted those into binary values using encoding. You could use label encoding or one-hot encoding depending on the feature. This is especially important for categorical data like gender, address type, and yes no responses. After that, we normalized the numerical values like study time and absences using standard scaling. This made sure all the features were on the same scale so that no feature was unfairly influenced so that no one feature unfairly influenced the model just because it had bigger numbers. We also dropped a few columns that added noise or didn't correlate well with the final grade. This made the model faster and more accurate. Here you could see I did grid search and randomized search. After choosing our machine learning models, we wanted to improve their accuracy by tuning their settings, also called hyperparameters. For example, with random forest, we can change the number of trees, how deep the trees goes, or how many samples are needed to split a node. And grid search, it tests every possible combination of parameters that we define. It's great for fine tuning because it explores all options in a systematic way, but it can take a lot of time if we give it too many choices, especially with more complex models. Randomized search works differently. It picks a random selection of parameter combinations from a list we provide. It's much faster, especially when we have a large range of values to test. While it may not find the absolute best combination, it often gets close enough and it saves us a lot of time. We use randomized search first to explore the wider parameter space quickly and get a sense of what works. Then we use grid search to fine tune around the best values found earlier. This combination helps us improve our model's performance without spending too much time on training. And as you can see here, the R2 score of the randomized forest is 0.77 and 0. It's around 0.77 with the use of grid search and um, sorry, grid search CV and randomized search CV. And if I had used the randomized forest alone, which you will see in a bit, the R2 score was around 0.76. So not much of a big difference, but it still went slightly higher. Here I for loop to go over the models and display the scores. And here you will see visualization of R2 score by model. R2 score is the coefficient of determination, which tells us how much of the variation in student grades our model is able to explain. Think of it like a measure of how well the model understands the data. Scores closer to 1 are ideal. In educational data sets, anything above 0.75 is considered strong. Our best performing models, especially random forest, achieved R2 scores above 0.75, meaning that they captured most of the patterns that affect student performance. That's a strong result, showing our model isn't just guessing, it's actually learning from the data. And here I went into a deeper analysis of the R2 score per machine learning model. Linear regression, it assumes that the data is linearly and performs well, indicating that a lot of the relationships in the data might actually be linear. For random forest, it explains over 76% of the variation in student grades. It handles nonlinear relationships and feature interactions well. It's strong for real world use, gradient boosting, slightly under linear regression and random forest, while gradient boosting machines are generally more powerful, and it could indicate that mild overfitting occurred and suboptimal hyperparameter tuning. This slightly lower score indicates that the model may have focused too much on minimizing residuals on the training set. Neural networks significantly lower than other models, indicating underfitting due to inadequate tuning, insufficient epochs, or architectural mismatches. Neural networks generally need more data and computational power to outperform traditional models. Here is the mean absolute error. The mean absolute error tells us how far off on average our predictions are from the actual grades. In our data set, student grades range from 0 to 20, so the error scale is important. And mean absolute error under 2.0, which is 10% of the final grade, is already considered reasonably accurate, but our random forest model brought that down to below 1.5. This means, on average, our predictions were less than 1.5 grade points off, making it a highly usable and precise tool for early intervention. And here is the slight analysis of each machine learning model. So, like linear regression, the average error indicating in predicting grades is 1.14 grade points. This is reasonable and serves well on baseline. Random forest, this is the lowest amongst all models, indicating the smallest average in predicting errors. Gradient boosting, the average error is slightly higher than random forest, but performing better than linear regression and neural networks. Neural network was the worst. It's the highest among all matters, suggesting a higher prediction error. We don't want errors in our data set, especially in machine, like when you compute machine learning models. You want to reduce the error as much as possible to make sure that your model is able to predict the predicted values accurately in observation to the y values. The root mean squared error. This is the visualization of the root mean squared error. It's similar to mean absolute error, but it punishes larger errors more. This is important because we care a lot about the big misses, like a student predicted to pass but actually fails. In our project, the root mean squared error below 2.0 indicates that even the largest prediction errors weren't far off from reality. Our top model stayed well under that threshold, showing consistency and reliability, not just on average, but across all students. And here is the deep dive per machine learning model. So for linear regression, you have slightly higher than mean absolute error, showing that the model is sensitive to some larger errors. The root mean squared errors penalizes those larger errors more heavily. The score being this low, suggesting that the relationships are largely linear. For random forest, we have reinforcing that the model makes fewer errors, captures the patterns and non-linearities well, making it robust to noise and outliers. It is an ensemble method that reduces variance by averaging multiple decision trees. Gradient boosting is also good, comparable to linear regression but worse than random forest, and sensitive to hyperparameter tuning. Neural network was far off with the largest errors, highest score amongst all the other models, significantly higher than other models, indicating large prediction errors for some students. And neural networks benefit from larger data sets and optimized training, as stated before. This is the grade distribution, the final grade distribution. The final grade ranges from 0 to 20. Most students scored between 10 and 15, showing average performance. Few students got really low or perfect scores. This distribution helps the model learn common outcomes better. As stated, most students scored between 10 and 15, suggesting an average to above average performance. Fewer students score below 5, which indicates failure or poor academic engagement. Very few students scored 19 to 20, showing that perfect scores are rare and possibly reflect high study time, strong family support, or high parental education levels. I attested that because my mother is a telecommunications engineer and she supported me from elementary school to college, and she was there for me, so I did good. As noted, we are getting a master's of science degree. There may be visible clusters around specific grade ranges, such as 10 to 12 or 14 to 16, suggesting potential thresholds in student engagement or school evaluation policies. Here is, I've created some visualizations of final grade by study time, by failures, and by sex. And here, as you can see, by study time, as the study time increases, the grade tends to go up, but it plateaus at between 3 and 4. So even as the study time goes higher, the grade plateaus at an average of 15. This is final grades by failure. So the more failures, the lower the score, which is a very bad outcome. Here is final grade by free time. The more free time you have to study, the grades tend to average at around like 14 out of 20. Doesn't indicate much, but I'm just putting it here as a representation that free time doesn't impact the score. I mean, it has a neutral correspondence to score. Here is the final grade by sex, male or female. The scores averaged out the same. Randomized forest versus randomized search and grid search. So random forest gave strong results without much tuning and is great at handling complex data. Grid search checks every possible setting but can be slow. Randomized search is faster and works well when you're unsure of the best settings, and using both helped us explore broadly and then fine tune. So grid search CV tests all of the combinations but can be slow, best for fine tuning when parameter ranges are known, and randomized search CV is faster and better for exploring large parameter spaces but may miss optimal settings. Combining both allows for broad exploration followed by targeted optimization to boost model performance. And in conclusion, Random Forest came out as the best overall model with a strong R2 score and low errors. Linear regression was also good and easy to interpret. Gradient boosting showed potential but needed more tuning, and neural networks didn't do as well because the data set was too small, as stated before. Important features were attendance, study time, and parents' education. Overall, this project shows that machine learning can help schools support students before they fall behind. And with that said, thank you so much for listening. I'm happy to answer any questions about the models, results, or next steps. I hope I get a good grade on this presentation. I know I went over 10 minutes, but it's hard for me to present a lot of data and analysis in such short amount of time. I hope you have a great day, and thank you, Professor, for this amazing class. I appreciated your time, and the learning materials were awesome, and I can't wait to become a great AI ML engineer. Thank you so much. Take care. Bye-bye. Hello?